All right, let's dive right into this explainer. Today, we're taking a completely mind-bending journey. We're going to scale all the way out to the absolute edge of the observable cosmos, a place where numbers get so incredibly massive they literally lose all meaning. And then? Well, then we're going to plunge completely inward, deep down into the subatomic quantum realm. Ultimately, we're tackling one overarching question today. How big is the universe really?
You know, to even begin to grasp our ultimate place in reality, we have to completely shatter our everyday sense of scale. Our brains are wired for a daily commute, not for understanding the sheer, terrifying volume of the cosmos. So we've got to ask, if we step back and look at the entire universe, just how big is it? And perhaps even more importantly, what are the fundamental rules that allow this colossal structure to even exist in the first place?
Part 1. The cosmic zoom out. So right off the bat, we have to quickly strip away everything you think you know about distance.
When you stand outside, the Earth feels infinitely vast, right? But to truly visualize our cosmic neighborhood, let's shrink things down to a manageable scale. Imagine the Earth is just a small green pea. On that exact same scale, the Sun is a giant inflatable beach ball. And how far apart are they? They'd be a full football field away, about 100 meters. Now keep walking. Our outermost planet, Neptune, on this same scale, would be a tiny sphere floating a full 3 kilometers away in the dark, freezing void. Think about that. That means 99.99% of our solar system is literally just empty space.
And it gets wilder. As we zoom out past Neptune, we hit the Oort cloud, which is this massive shell of icy debris bordering our solar system. The Voyager 1 spacecraft has been traveling since 1977, and it still hasn't cleared it. At this point, kilometers become completely useless to us. We have to rely on a staggering new measurement, 9.5 trillion kilometers. That is the vast distance that light travels in a single year.
Now, the absolutely crucial thing to understand here is that a light year isn't just a measurement of space, it's a measurement of time. Because light takes time to travel, looking at our neighboring Andromeda galaxy, which is 2.5 million light years away, means we're essentially using a time machine. When you look at Andromeda in the night sky, you aren't seeing it as it is today. You are literally looking 2.5 million years backward into the past, way before modern humans even walked the Earth.
Part 2. Rivers of Galaxies. But hey, our solar system is just the beginning. Let's see how this local neighborhood builds and flows into massive networks of stars as we leave our galactic backyard.
Think of this as our true cosmic address. Our Sun is just one average star sitting in the quiet Orion arm of the Milky Way, and our galaxy boasts over 100 billion stars. But the Milky Way itself? It's just one part of the local group, a neighborhood of about 50 galaxies. That group flows into the Virgo cluster, which is then swept up into the Laniakea supercluster, a massive structure 500 million light-years wide containing 100,000 galaxies. And Laniakea? It's just a tiny thread in the cosmic web, a giant 3D spiderweb of galaxies spanning megaparsecs across the universe, all separated by giant, empty voids.
Part 3. The Edge of Infinity. As we zoom out further to the absolute limit of human perception, our sense of scale gets truly mind-boggling. Where does this web actually end? Well, this brings us to a staggering wall, 93 billion light-years. That is the diameter of the observable universe. Because the universe has been expanding for 13.8 billion years, this is the absolute maximum spherical boundary of ancient light we can currently perceive from Earth. Inside this bubble, trillions of galaxies. Outside of it, there could be an infinite expanse, a universe without an edge, or maybe even a multiverse of countless other bubbles. We simply cannot see past this wall of light. Okay, but here is where we execute a hard pivot. We've looked out into the macro scale, this infinitely vast cosmos. But to explain how this colossal structure survives, and to answer the fundamental question of why there is anything here at all instead of just a cold, empty void, we have to look in the exact opposite direction.
Part 4. Zooming into the quantum. To find that answer, we actually have to leave the stars behind, dive deep underground, and explore the rules governing the very smallest particles in existence.
To understand the cosmos, we actually have to go 100 feet beneath the border of France and Switzerland to CERN. On the macro scale, we have a 93 billion light-year universe. On the micro scale, we have the Large Hadron Collider, or LHC. It's a 17-mile frozen tunnel where magnets colder than outer space steer protons into head-on collisions at 670 million miles per hour. For just a flicker of a second, these subatomic car crashes create a quark-gluon plasma that's 100,000 times hotter than the center of the Sun. It's literally a tiny perfect echo of the universe just a fraction of a second after the Big Bang.
Scientists build these echoes to test the Standard Model. Now, this is the ultimate physics rulebook. For 50 years, it has accurately predicted what everything is made of. It famously predicted the Higgs field, which is this invisible field that drags on particles to give them mass. Without the Higgs field, the atoms in your body wouldn't have any weight. They'd just rocket around at the speed of light, and planets wouldn't even exist. The Standard Model is arguably the most successful idea in science, but scientists know it's missing pages, because it doesn't explain gravity or dark matter.
But recently, scientists spotted a massive crack in those rules. The LHCb detector spotted something called a penguin decay. Side note, it's called that because a physicist lost a game of darts in the 70s and had to sneak the word penguin into a scientific paper. Anyway, this decay is a highly rare, 1 in a million event where a heavy, unstable B meson particle shatters into a kaon, a pion, and 2 bulky muons. The rulebook strictly dictates the exact angles those bulky muons should fly away at, but the collider caught them flying off at completely wrong angles.
So what really matters here is how scientists measure this anomaly. They call it a 4 sigma event. That means there's only a 1 in 16,000 chance that this is just a random fluke. Even wilder, a second completely rival detector called CMS confirmed the exact same misbehavior. But scientists are notoriously paranoid about false alarms. They demand a 5 sigma certainty, which is a 1 in 2 million chance, before officially declaring a discovery. Why? Because years ago, a supposed ghost particle caused scientists to write 500 papers before it just vanished with more data. So for now, this anomaly could be a brand new, undiscovered force of nature tugging at reality, or it might just be a ridiculously complex mathematical smudge they nicknamed the charming penguin.
Part 5. Escaping the annihilation. Now, what's incredibly interesting about this subatomic puzzle is how it directly relates to your ability to sit here and view this explainer today. According to the strict rules of physics, the Big Bang should have created perfectly equal amounts of matter and antimatter. And when matter and antimatter touch, they instantly annihilate each other in a flash of light. By all accounts, the universe should be an empty, cold void. But it's not. Somehow, a microscopic imbalance occurred. For every 1 billion antimatter particles that were destroyed, exactly 1,000,000,001 matter particles were created. That tiny, fractional edge allowed matter to escape complete annihilation. When you look up at the night sky and you feel overwhelmed and small in a 93 billion light-year wide universe, remember this: your very existence gives you massive cosmic weight. You are made of the 1 in a billion that lived. You are the rare survivor of a subatomic quantum war that built the galaxies, the stars, the Earth, and ultimately, you.
So to wrap up our explainer today, I want to leave you with this final thought. We live on a tiny pea of a planet, spinning inside a cosmic web that stretches way beyond our wildest imagination. Yet we are intricately tied to the deepest, most microscopic quantum mysteries of existence. If the missing physics at CERN finally crack the Standard Model and reveal what tilted the scales of reality to let us exist, what do you think we're going to discover when we finally read the hidden, missing pages of the cosmos? Thanks for joining me on this journey. Keep looking up and keep questioning.